Assalamu alaikum. Today we will talk about the boundary conditions for electrostatics. In electromagnetic theory problems, sometimes the field quantity effect will be present in two different media, and these two different media have a different electromagnetic properties. In such these cases, we wish to determine how these different vector quantities like the electric field intensity E and the electric field density or the electric displacement D, how these vector quantities change in crossing this interface between these two media. In a previous video, we have talked about the boundary conditions at free space conductor interface. I'm going to leave the link of this video in the descriptions. Okay, let's start. To determine the boundary conditions, we usually invoke source equations, or namely the divergence and the curl equations. Okay, we know that the divergence of the electric field in electrostatic cases is equal to 0, and the divergence of the electric field is equal to rho divided by epsilon, where epsilon is the electric permittivity and rho is the volume charge density. Firstly, we are going to start by determining the tangential components of the electric field, okay, at the interface between two different media. In this illustrative figure, you see we have two media, okay. In each media, we have a different electric field quantity vector, E1 and E2. And corresponding to this, we have also a different electrical permittivity. In this, we have epsilon 2, which is the permittivity in this media, and epsilon 1, which is the electric permittivity in this medium. For tangential component, I'm going to invoke the curl of the electric field, which is equal to 0, and by applying Stokes theorem, we understand that the line integral around some closed contour, around some closed path, is equal to 0. So from this equation, you see I'm going to take the line integral for the electric field. Okay, for this I'm going to draw some path between these two media, and you see that I called this path by ABCD. This path has width of delta W, okay, and it has the height of delta H. I'm going to determine this unit vector A sub n, which is a normal unit vector to the interface between these two media, and this A sub t is the unit vector which is parallel to the interface. The method that we will pursue to determine the tangential components is taking the integral around the draw closed path and make delta H approach 0, and consequently we will end up with only the components parallel to the interface. Now let's start integration. Firstly, I will start with this path from D point. Okay, we have this D with this small line path DC, which has the width of delta W. Okay, you see that the electric field in this part is E1, and it's dotted with this line path. As you see, this path is a vector, so I'm going to determine some direction. I make the direction counterclockwise. It doesn't matter. Anyways, E1, okay, dotted with this small path, which is delta, which has the magnitude of delta W, and its direction is the same of the direction of AT, this parallel unit vector A sub t, plus just according to CB and AD paths, just leave them to the end. I'm going to go to this part of path, which is BA. Okay, in this part of path we have the electric field vector ET present, okay? So E2, okay, dotted with this path, which is AB. This path has magnitude of delta W, and its direction is opposite to this unit vector AT. So it's minus AT. Okay, now regarding to the rest of paths, CB and AD, I'm going to denote the contribution of the line integral at these two paths, AD and BC, and by X, okay? X, as I said, is the contribution of the line integral at these small paths, CB and AD. And all of this is equal to 0. Okay. Now, as we aforementioned before, we want to make delta H approach 0. Okay? Because we want to find the electric field at this interface only. And accordingly, this contribution of the line integral X is going also to approach 0. So accordingly, this is going to vanish, and we will have, I want to simplify this formula. What is the dot product between E1 and the unit vector AT? So basically, the electric field E1 is equal to the summation of two contributions of vectors. It's equal to the summation of E1 sub t, or the tangential component of this electric field, plus E1n, which is the normal component of the of E1 vector, and the same thing for E2. And this component of the electric field E1t is tangential to the interface, so it has the same direction of the unit vector AT, okay? And its magnitude is simply E1t, and the same. And regarding to the normal component E1n is orthogonal to the interface, so it has the same direction of AN unit vector. So, and E2 also will have the same components like ones for E1. Anyways, the dot product between E1 and the unit vector AT will make the normal component of the electric field vanish. So we will have only E1t. And regarding to this, we have also minus E2t. This equation can be rewritten as, and from this equation, you will notice that the tangential component of the electric field at medium 1 and medium 2 is the same. So we understand that we have no discontinuity at the tangential components in the interface between two different media. By other words, we can say that the tangential component of the electric field is continuous across an interface. And as we know that D1, the electric displacement, okay, the electric displacement in this medium is equal to the permittivity in this medium, which is epsilon1, times the electric field in this medium, and D2 is equal to the permittivity in this medium times the electric field in this medium also. And accordingly, we can write the tangential components for the electric displacement, okay, in this way. Now let's find the normal components for the electric field. To determine normal components, we are going to invoke the divergence of the electric field, which is where rho is the volume charge density. In some textbooks, they are using a different symbol, but in our case, we are going to use rho to denote the volume charge density. We know that the electric displacement is equal to, so accordingly, we can rewrite this divergence equation in this form. Okay, I will start finding the normal components by applying the divergence theorem by taking the volume integral for both sides. the volume integral for the volume charge density is equal to rho, the volume charge density, times V, okay, which is the volume, and the answer of the multiplication is equal to Q, which is the total charge in the in some volume, okay. And regarding to this, the volume integral of the divergence is equal to the surface integral for the electric displacement around some closed surface. From this equation, we see that we want to find the surface integral for the electric displacement, so that we are going to I'm going to draw a surface, okay, between which is extending through this media, through these two media. The upper and the lower surfaces of this cylinder have some area of delta S, okay, and this cylinder has a height of delta H, okay. And as we determined before, the unit vectors for the tangential and normal components, I'm going to write them. The tangential component is pointing to this direction, okay, which is parallel to the interface, and the normal component is directing in this way, which is normal to the interface between these two media. And the same operation that we did before, we are going to apply in this case. We want to find the normal components at only the interface between these two media. So we are going to apply this integral, then make delta H approach 0. Okay, let's start. We are going to make dot product between the electric displacement and the differential surface. You see that we have three surfaces: the upper and the lower surfaces of the cylinder and the curved wall of this cylinder. I'm going to start with the upper surface. For the upper surface, only D2 vector is present, okay, so we have D2, okay, dotted with the vector area of this surface. The vector area has magnitude of delta S, which is the area of this surface, and and its unit vector is normal to this area, okay, like this, which is simply the same of AN, okay. Now regarding to the lower surface, we see that D1 is present in this case, dotted with, and its unit vector, okay, it's like this, which is equal to minus AN. And regarding to the curved wall, the contribution of the surface integral, for the curved wall is equal to Y. Okay, let's assume that the contribution from the curved wall is equal to Y. Anyways, it's going to be eliminated at the end, equal to Q. As we aforementioned, we want to make the height approach 0, and accordingly, the curved wall of this cylinder is going to be lessened. So this contribution is going to be lessened also. So accordingly, Y is going to approach 0. So we will have, by dividing both sides by delta S, Q is equal to the total charge enclosed in this cylinder. Q divided by delta S is equal to the surface charge density at the interface, okay? So I said that I'm going to use for charge density the simple rho, but to distinguish it from this volume charge density, I'm going to use the subscript S to denote the surface, okay? Okay, this final result is satisfying to us, and it's clear, but we can rewrite it with more clear way. We said that these vectors is equal to the summation of tangential components and normal components, okay? The dot product between D vector and normal unit vectors will yield only normal components, and tangential components will vanish. Okay, And from this equation, we see that the normal components for the electric field or the electric displacements are discontinuous across the interface, and this discontinuity is equal to the surface charge density. But when two dielectrics are contact with no free charges at the interface, or by other words, when ρs is equal to 0, then d2n minus d1n is equal to 0, or d2n is equal to d1n. So the normal components of the electric displacements are continuous when we have no surface charge density at the interface between these two media. So finally, I'm going to write the final deduction that we have found. And to summarize what we retrieved in this lecture, we can say that the boundary conditions at the interface between two different media is as follows. The tangential components are continuous and the normal components are discontinuous, and the discontinuity is equal to the surface charge density of the interface between these two media. And that's the end for today. See you.